So today we would like to talk about two-stage optimization. As I mentioned before that one type of design optimization will be nominal the best, which means that the designer or the engineer prefer the output to be at a fixed certain value, not too high, not too low, but exactly right there. It is called nominal the best. Previously, we often just use analysis of mean to find out the relationship between control factors and the output. And then from the effect plot, we find out a combination that will optimize our SN ratio. In the previous example, I just did you to go through using that cantilever beam. We know that after this first stage optimization to find out the maximum SN combination, which will not guarantee our output will be at the target value. Therefore, in order to move this output value to the target value, we need to do the second stage optimization. This is what I'm going to introduce here. So for nominal the best problem, we know that we have a mean square deviation using this equation. And by using mean square deviation, we can come up the SN ratio. As I mentioned before, that the mean square deviation for nominal the best will include two parts. The first part is the difference between the average output to the target value. M is the target value. S is the standard deviation. Therefore, in order to minimize mean square deviation, it will be better that Y will be right at the target. So this term will cancel out. However, when we move this average value to the target, we need to make sure that our SN ratio will remain the same. Or I should say that in our nominal the best, if we want to adjust the value using the scaling factor, as I mentioned before, that scaling factor has a property that when we move that factor, the output standard deviation and output mean will remain constant. Therefore, if they are remain constant, the SN ratio for nominal the best will remain the same because in the quotes, it is average divided by standard deviation. So that's the reason we want to find out a scaling factor and using that scaling factor. Scaling factor is one of the special control factors to move the output Y bar to the average value in such a way that we can have our output right at the target. But since it is using scaling factor, this value will remain constant when we do the adjustment. Therefore, SN ratio will remain the same because after the first stage optimization, SN ratio already will be the maximum value. So when we do the second stage adjustment, we don't want to influence our accomplishment in the SN ratio. So the second stage optimization is to initial design right here. So after this first stage optimization, we minimize, or we should say that we maximize the SN ratio. So this average value will move to a certain value. As I show you in the last example, the average output of that cantilever beam will not be right at the target, right? Remember the last example I just lead you through. So for the last example in the using Excel, we want to optimize the cantilever beam. And the output for the cantilever beam is required that the stiffness will be 1. And from the analysis of mean, we can get the maximum SN combination. This is the combination will have the maximum SN. And that was the initial design. As you compare here, you can find out that the average output for the initial design is 1 right here. 1. But after the first stage optimization, the optimum design, the average value for the optimum design, average value will be 0.89, right here, 0.89, which is not on a target. So if you are a designer or if you are the user, you'll be kind of unhappy to buy, for instance, a cantilever beam, and you ask the cantilever beam to be K equal to 1, but you have K equal to 0.89. So in the second stage optimization, we want to move our average to target. So the second stage, we need to move our average to target, right? This is the target. During the moving, we want to make sure that our maximum SN will remain the same. But we can adjust the value to here. That is the reason we want to use a scaling factor. And this is the property of the scaling factor. We mentioned that before, that this is the scaling factor, this is output. And when we change the scaling factor, the output will change. But also, the standard deviation of the output will also change. And this change will remain a constant. That's the reason why when we adjust the scaling factor, our SN ratio will remain the same, because this is the constant if we are using scaling factor. Okay, it's right here. If you are using scaling factor, that will remain the same right here. Okay, let me adjust the pointer a little bit. And this is how we classify the control factors. As I have already shown you that, we can classify the control factors into 4 categories. And we are looking for the third category, because in the third category, that control factor will affect mean, but will not affect SN ratio. So that's how we choose the control, the scaling factor at the second stage optimization. And this is how we select the scaling factors. We need to select a scaling factor which will not be too expensive to adjust. And also, it cannot be a discrete variable, because if it is a discrete variable, it cannot be changed continuously. So here in this case, in our last case, we find out that only H is the type 1 control factor. And the rest of the factors, you can see B, H, L, they all have the influence on the mean output, but they have a very small or almost non-influence on the SN ratio. They are very small. So I will say that only H will be the type 1, but B, L, E, they are all type 3, which could be scaling factors, but we only need 1 scaling factors. Okay, so we only need 1 scaling factor, and I mentioned before, E is the discrete variable, is material properties, cannot be used as a scaling factor. And B and H, which is the width, the B is the width, and L is the length of the cantilever beam. I assume it will be easier to adjust the length than adjust the width. So we choose L to be the scaling factors. Here, before we want to, so this is the noise level, which is the 3 noise factors in this example, only 3. So we are using this one, L9 and L4 cross array experiment. Since only 3 noise can fit in L4, because it can accommodate 3 noise factor maximally. This is the result in the slide and also in the videotape. And so we can use the first, for instance, this is how we did that, and I already showed before. And this is the SM effect plot. Okay, and this is the optimum design. And we need to verify the optimum design. And this is the output. And this is the average of the optimum design, the K only equal to 0.89. but our nominal design is k equal to 0. So we want to move our average to target. How can we adjust the output? Move the average to target, but we don't want to mess up the SN ratio. We want to keep the SN ratio to be the maximum. Therefore, we choose scaling factors. From that previous example, we know that we have type 3 factors. We only need one. So we need to select which one will be better. Young's modulus is a discrete variable, so it is not good as scaling factors. And as I mentioned before, adjust L will be easier than adjust B. So we choose L to be the scaling factors. Then we can try and error to manipulate or to adjust the length L in such a way that K will be equal to 1. In this way, we choose KL to 52, and we find out that the average will be just exactly 1. I will show you using the Excel, and we can compare the result. As I mentioned before, this is the initial design from the questions. And what will be the optimum design? After our first stage optimization, our optimum design average will be 0.89. As you can see, the standard deviation has been reduced. SN ratio has been maximized. But this is not on the target k equal to 1. So we want to move this one to here by choosing the scaling factor length, L. So we adjust L and find out the optimum design. This is the optimum design. Average will equal to 1, and this is the distribution of the optimum design. As you can see, if we compare the initial and the optimum, they all have an average value k equal to 1, but for our optimum design, it has a smaller standard deviation, which shows that our optimal design will have a better quality performance than the initial design. Okay, this is the two-stage optimization. Let's finish that Excel example we left out last week. And this is the result after the first stage optimization. Therefore, we need to choose which one will be the scaling factor. Okay, this is the effect plot for average output. This is effect plot for the SN ratio, and this is for average output. So from these two plots, you can see the conclusion will be the same, even though we changed the outer array into L8. It was L4, but you are working on L8. So you can see that we still have one type 1 control factor, which is H, 3 type 3 control factors, and we only need one. So we also based on the same reason, we also choose L length to be the scaling factor. Okay, so at the second stage optimization right here, let's look at the design. Our design will pretty much follow the optimum design from the first stage. So we copy the result over here and pass it, pass the value. But we want to adjust one scaling factor, which is the length here. The length, right? It was 54. And let's again do the simulation. How to do the simulation? We are using L8. So here we already make sure our equation will be correct when we copy that over. So we still copy the equation downward, and we haven't do any adjustment yet. So you can see optimum design right here before adjustment. So we want to adjust this number in such a way that our average output here will be 1. Right now it's 0.89, right? So we want to adjust this one to make it 1. First, you have to know that because this is equation, we can try and error randomly. But in the real world, any adjustment will stand for one experiment, which means that you need to pay money to get the data. So we want to make sure our adjustment is correct. For instance, we want to adjust L. Should we make L bigger in such a way that the average will be closer to 1, or should we make L smaller in such a way M will be close to 1? Should we try L to be bigger or smaller? Which direction should we try? At least we can go to the right direction, although we don't know how much we should adjust. But should we make it bigger or make it smaller? Some of you might be confused why I ask you these questions. But what if you already know the direction? When we move L bigger, if K will increase or decrease? Don't look at me, look at the effect plot. Right? You already make an effect plot here. This is the effect plot for the L on the average output. So if you make L bigger, what happened to K? You become smaller, right? If you make it bigger, K will become bigger. I'm sorry, smaller. If you make L smaller, K will become bigger. Therefore, you can get the information from the effect plot, how L influenced the output. So, because right now it's 0.89, we are choosing L1, 0.89. So if you want to make it bigger, you should reduce L to a smaller number rather than increase L. At least you are going to the right direction. So let's try smaller number like 53. Enter. Let's try. How does it work? Okay, good. See, I changed it to 53. It moved to 0.94, closer to 1. And it also, we are moving to the right direction. It was 0.89, now become 8.94. Remember, every try stands for money. How about smaller? Let's make it 51. Oops, too much. A smaller number, even smaller number, 51. But the output will become, as you can see, right now it's over 1, 1.06, too big, 1.06. So it's a number between, if we try 53, right? It's a number between 51 and 53. 51 too big, 53 too small, so there'll be something in between. You can keep trying, and let's try 52. And you can find out that, because I tried that before, you can find out that, ooh, perfect. The output will be almost exactly to 1. There might be a small number in the 5th or the 6th decimal, but doesn't matter. Any questions? This is how we work. So after the adjustment, after the second stage of the optimization, we find out that we can keep everything the same as the maximum SN ratio design at the first stage. But in the second stage, we only adjust this scaling factor L. Let's make it red. We only adjust this scaling factor. And the output become 1. Let's double check what happened to the SN ratio. Initial design 22.75. After the first stage optimization, SN ratio become 23.29. You can compare this one with the L9 sample. You can find out this is the biggest SN ratio, right? Although this one very close, but it is still the maximum. Good. And after the second stage, we adjust these scaling factors. What happened to average? Right at the target, perfect. But how about SN? Well, it dropped a little bit. You cannot make sure that this scaling factor has no effect on SN, but a very small. So it does drop, but 23.28, still very close to the optimum SN. And better than that, this one will have the average one, just like the initial design. But when you compare these two, you can find out the standard deviation 0.69 is smaller than 0.73 of the initial design. This is how it works for the two-stage optimization. Any questions? All right, let's go back to the homework. So here for homework number 4, we pretty much finished everything. But here he wants you to classify the control factors, right? We already did that last week. And he wants you to select one scaling factors. You need to discuss how do you select the scaling factor. You cannot say, okay, I want to pick L. Just like the class note, we classify, find out that there are 3 type 3 control factors, which will be B, L, and E. Just like what we discussed in the lecture notes, you should say why there are 3 type 3 factors. You choose L to be the scaling factor. Because no discrete, because you want to choose a cheaper variable to adjust. So you pick L, right? The third one, adjust the scaling factor to move the mean to target. We already did that. And we found out when we change L into 52, average will be right on the target. Compare the SN for the initial and optimum. So you pull the number out, initial design, what will be the SN ratio? And for the first stage optimization, it will be 23.29. But after the second stage optimization, it still remains a very good number, 23.28. You can compare these two. This is better than the initial design and has the same target average output. And the last one, as usual, like what you did in the like I play example, we want you to draw the probability density curve for the K to compare the optimum result. You can do the same thing like what I did in the lecture note, but you can only compare the initial and the optimum. This is pre-optimum, the first stage optimization, but the only purpose is want you to compare these two. So you can just draw these two. If you already draw 3 curves, they will be fine. But at least you need to draw these 2 curves to show that this is the initial, this is the optimum after 2-stage optimization. Average, the same, but the standard deviation is smaller, which means that the conformance is better. There will be the end of the homework number 4. Any questions? Let's take a break now. Okay, and come back at 10:30. Then we will continue on the next chapter, which will be compound noise factors. Okay.